All right, so just to kind of re-summarize that here, we end up seeing that the fluid in the distal tubule is lower than the osmolarity that we started to begin with. So just jumping back here really quickly, we started out with an osmolarity of 300 milliosmoles. We end up with an osmolarity that's extremely low. It's 100 milliosmoles, right? And so what we're seeing now is at the distal part of the loop of Henle, we now have this gradient, right? We now have the plasma having 300 milliosmoles in terms of the osmolarity, whereas our filtrate has 100 milliosmoles in terms of that osmolarity. So we've also set up another gradient in terms of our tubular fluid in the distal convoluted tubule compared to the plasma in the peritubular capillaries that are surrounding that distal tubule, okay? So just to recap that here again, the medullary interstitial fluid increases from the cortex down to the renal pelvis, but then also our tubular fluid goes from 300 milliosmoles coming from the proximal tubule all the way to about 12 to 1400 down at the deepest part of that tubule, and then back up to 100 milliosmol in the distal part of the tubule. Okay. All right, so let's walk through how we kind of put all this together and establish these conditions, right? So let's talk about how we start out here. So we're starting out with the scenario where we've got fluid coming from our proximal convoluted tubule. It's moving down into the loop of Henle. It's starting out at an osmolarity of 300 milliosmoles, okay? And this is all theoretical, by the way. This is kind of just hypothesizing how we end up with the scenario that we see. And so this is just a stepwise scenario to hypothetically discuss how we establish that gradient, okay? So we push fluid in here. It's starting out at 300 milliosmoles. And because the ascending limb is only permeable to our solutes, we start out by actively pumping sodium, chloride, potassium from our tubular filtrate across into the medullary interstitial fluid. And so that's the first thing that we do. So we increase the osmolarity of our interstitial fluid in that way. All right. Because we've pumped solutes out into this region to start, we now have a gradient, right? So we've got more solutes that we've just actively pumped out in our interstitial fluid around the medulla. And so now, because the descending limb is only permeable to water, that water is going to naturally want to go to this area that has higher solute concentration. So we've got an osmolarity of 400 milliosmoles out here because we've pumped solutes out, and then water having an osmolarity of water moving into this interstitial region. Because it has a lower osmolarity of the filtrate in the tubule, it's going to passively move out into that region. The next thing is that we end up with this isoosmotic state. And so we have an osmolarity in our interstitial fluid of 400, an osmolarity along the descending limb of 400, and an osmolarity along the ascending limb of a lower amount, which is about 200, okay? The next thing happens, we then, again, pump more solutes out. So more of those solutes enters the interstitial fluid actively being pumped across that membrane, and then more water can follow, right? So more solutes pumped into the interstitial fluid across the descending limb, more water passively follows. And so once again, we see our osmolarities change here. So because we've pushed more fluid down, the fluid that's at the bottom of our tubule, where more of that water has left, now has a higher osmolarity. The fluid that's just coming in at the top has not had an opportunity for that water to leave just yet, and so it has a higher osmolarity, okay? And then we end up at steady state once again. So looking at our values, we're starting to see this gradient emerge, right? As we push more fluid down into our tubule, which is starting out with an osmolarity of 300, and there's less time for that equilibration to happen, for solids to move, for water to move, we start to see this gradient emerge, right? So up here we have an interstitial fluid osmolarity of 350. Down here, where there's been more time for water to move, we have an interstitial fluid osmolarity, of about 500. Same thing here in the ascending limb. because we're coming from that fluid that is a higher osmolarity here in the descending limb. Remember, if more water is moving, we're having a higher osmolarity as we go deeper into the descending limb. But as we're moving more solutes across this end of the limb, that osmolarity is going to decrease once again. So as it begins decreasing, we see a higher osmolarity at the initial part of the ascending limb. But as more time has been allowed for solutes to leave, we see a lower osmolarity toward the end of that ascending limb, okay? And that goes on again and again and again until we establish a steady state. And a steady state means that the values are not changing even though I'm introducing more of that fluid into the loop of Henle. And so at that steady state, we see this gradient that has been completed quite nicely. So our filtrate starts out at 300 milliosmoles. Because it's going down deeper into the medulla to the loop of Henle here, and more water is being lost as it progressively moves down, we see the osmolarity gradually increase, right? So it goes from 300 up here all the way down to about 1400. And then according to the descending limb, because we see the active movement of solutes happening, our gradient is moving in the opposite direction. So we go from 1400 milliosmoles here, which is really concentrated. And as more of those solutes leave, right, as that goes up the ascending limb, we go back down to about 100 milliosmoles, all right? Okay. I'm going to pause here and see what questions we have about that, about establishing the measured osmotic gradient. Okay. Okay, so question here, do solutes go down the descending limb with water, but they can't get out because it is only permeable to water? Yes, excellent. That's a great way of expressing that. So because the solutes cannot leave down the descending limb, they're kind of trapped there. That's why the osmolarity gradually increases. The water can leave, but the solutes cannot. Opposite is true across the ascending limb. So because the water cannot leave, the water is trapped, the solutes are leaving, and the osmolarity moves in the opposite direction. Okay, let's see. Okay, good question there. Any other questions? Any other questions on this? And so we want to think about, just to kind of reiterate this again and add some more details, we want to think about the gradient that is being established of our filtrate. So our filtrate goes from 300 to 1400 back to 100. And it's really important that this number ends up being lower than 300. I'll talk about that going forward. But then we also want to think about the gradient of the interstitial fluid of the medulla, which is not the filtrate, right? So outside of the filtrate. So we go from 300 up here all the way down to 1400 down here as well, okay? So there's really two gradients that's happening here. A gradient of the fluid that's moving through the tubule, through the loop of the tubule, but also a gradient of the interstitial fluid that is surrounding that tubule. It goes from 300 around the cortex all the way down to about 1400 in the deepest part of the medulla, okay? All right, let's talk about the role of urea here. And I sort of began speaking about urea earlier. Urea is one of those byproducts from proteins. It's processed in the liver and then it ends up in our plasma. And it's really important that it is eliminated from the body, one, but it is also important that it is existing in our tubular filtrate because it has a really important role to play as far as establishing that gradient as well. So urea is being pumped, or not pumped, it's being moved across the collecting duct by these UTA transporters. It is water soluble, and because of that, it's going to be passively moved across this collecting duct, but then it's also going to move into the plasma here, into our vasa recta, the ascending limb of our vasa recta. and it's going to help to increase the osmolarity of the capillary here. So going towards the distal, the peritubular capillaries that are going around the distal convoluted tubule. It's also important that we increase the osmolarity going in this direction, okay? And so we've got this urea that's present, that's being moved out of the collecting duct and into the plasma to help create that, that concentration, to help create that osmolarity in order to facilitate the gradient that's in this part of the vasa recta, okay? Before we kind of get into the details of that, I do want to explain what's happening here, because this is another point of confusion that students often raise, is that we have the ascending limb and the descending limb of the loop of Henle going in the opposite orientation of the ascending limb and the descending limb of the vasa recta. Okay, so let me say that again. So the descending limb of the loop of Henle actually is coming in contact with the ascending limb of the vasa recta. Okay, so they're going in opposite direction. That's going to be really important in understanding how we move the fluid and the solute that we've just been talking about into these different parts of the vasa recta. So we've got the ascending limb of the loop of Henle on the other side, right? So going toward the distal tubule. This is coming into contact with the descending limb of the vasa recta. And this is where we see that that urea being moved from the collecting duct back into the vasculature here to facilitate that movement of water. Remember, water is moving, solutes are moving in this direction. And so in order to keep the gradient within the vasa recta, we see the movement of this urea into the descending limb of the vasa recta, which is facilitating that movement happening in the ascending limb of the loop of Henle. Okay. I hope I didn't further confuse you, but that may make a little bit more sense as we keep going here. So what we're going to speak about now is what's happening in the vasa recta, okay? And so really bear in mind, as I'm speaking about the descending limb of the vasa recta and the ascending limb of the vasa recta, they're coming into contact with the opposite component of the loop of Henle, of the tubular structure. All right, so the anatomical arrangement of the vasa recta capillaries prevents the diffusion of the water and solutes from dissipating the medullary osmotic gradient. And what that really means is that in order to keep that gradient that we just worked so hard to establish, we've got to have the solutes moving in the opposite direction in our vessel. Otherwise, we would just lose that gradient, right? If I had water moving out my descending limb of my tubular fluid and then moving into the descending limb of my vasa recta, I would just lose that gradient, right? The medullary interstitial region would not establish and maintain the gradient that I just worked so hard to establish. So it's really important to have that opposite anatomical arrangement of the vasa recta in terms of the structures that are coming into contact with the loop of Henle, okay? So the descending limb of the vasa recta has an osmolarity of 300 to start. As it descends, water is going to leave, right? And again, please make this connection. You can even make it here in your notes. As this water is leaving, solutes are entering. And where are the solutes coming from? They're coming from the ascending limb of the loop of Henle. So really make that connection that the descending limb of the vasa recta is accepting the solutes that are coming from the ascending limb of the loop of Henle, all right? And as we go further down, our osmolarity increases in the vasa recta. Okay, so water is leaving by osmosis and solutes are entering from diffusion, but really important to understand where those solutes are coming from because of the anatomical relationship between the descending limb of the vasa recta and the ascending limb of the loop of Henle. On the other hand, we see the opposite scenario happening with the ascending limb of the vasa recta. Because the ascending limb of the vasa recta comes into contact with the descending limb of the loop of Henle, this is where we see that water entering. So water that's coming in here is actually coming from the descending limb of the loop of Henle, right? So water moves in, right? Solutes are going to be moving in the opposite direction. And we would tend to lose our osmolarity here. This is where we would tend to lose our osmolarity, this ascending limb, hang on, here. Yeah, so we're going up the vasa vector here. This is where we tend to lose the osmolarity of our gradient. So the ascending limb of the vasa vector is going to be where we're seeing that connection with the descending limb of the loop of Henle. And because we don't have those urea transporters here, we see that there's a higher osmolarity here because urea is being moved into this limb of the loop of Henle and not into this limb of the loop of Henle, okay? So we've got urea transportation happening on this end, but not on this end. And so the osmolarity ends up being higher here as we move water into our fluid, and then solutes are moving out in the opposite direction. Okay. All right, I'm going to pause here and see what questions we have on this. So it's really important to understand that anatomical connection first, in order to really understand why things are moving in the different directions here. But then also think about us not losing our gradient. So having that anatomical relationship is what is going to help us maintain that gradient. Okay. All right. I don't see any questions popping up, but if you're working on questions, you can keep those coming. We're not going to say much more. I don't want to overwhelm you because this is kind of, quite a lot to absorb so far. And so we'll see how much of this we have questions on, and then we'll pick this up next week. Okay. All right, I don't see any questions coming up. All right, in the last few minutes here, I'll just kind of reiterate what's really important in terms of you really understanding and what will be tested on your exam. So you should have an understanding of how we establish this gradient, okay, via the counter current multiplier. So you should definitely understand what the counter current multiplier is. This idea that the descending limb is permeable to only water, the ascending limb is permeable to only solids. You should also have an understanding of the gradient, right? So the fact that we're going from high to low as you go from the cortex down into the medulla. And then the other thing you want to connect here is that the purpose of this is to end up with a lower osmolarity of our filtrate over here in the distal part of the loop than what we start with over here in the proximal part of our loop, okay? When we kind of step back and think about the main role of the loop of Henle, it is to concentrate the urine, okay? And we do so by setting up this gradient. So water is leaving across the descending limb, solutes are leaving across the ascending limb, but this is only a part of setting up this gradient where we now have a lower osmolarity for our filtrate. What we're going to talk about later on is how now, because we have a lower osmolarity of our filtrate, water can leave freely through the rest of the tubule. So the loop sets up this condition where we can fully concentrate the urine because we no longer have this isoosmotic scenario that we started with. We now have a gradient here. So the gradient that we've created down here is really not the important gradient. The gradient that we now have at the end of the loop of Henle, where the filtrate is less concentrated. So water will naturally leave that filtrate more easily. That is the more important gradient. That is kind of the big picture of what the loop of Henle is doing, okay? But as a part of getting that, we still want to understand the countercurrent multiplier as well as that medullary osmotic gradient and really the why of why we set that up and how that ends up helping us concentrate the urine.